Now let's talk about conservation of energy. So far we have talked about kinetic energy or energy of motion. We have talked about potential energy of position in terms of gravity or strings. We have chemical energy and nuclear energy, which we haven't talked about, and we have electrical energy and magnetic energy. We have stored energy and light energy, and we also have heat energy. In mechanics, we need to worry about only the underlying energy forms, which are kinetic, potential, and heat. Other ones will appear later, and we only worry about heat if there's friction or drag. If the kinetic energy changes, let's say it increases, then the potential energy also changes. It will decrease in this situation in such a way that total energy change is zero. This is called conservation of mechanical energy. Another way to put it is the total energy of a system never changes. As we said in the first illustration, the change in kinetic energy and the change in potential energy together make total energy change equal to zero. That's if there is no friction or drag. Let's look at an example. Suppose the speed of a 2 kilogram ball is 15 meters per second when it reaches the bottom of a 20 meter tall track. Find the loss of mechanical energy and its location. So here we go, it moves and it goes. So this delta H will be 20 meters. So we know that from conservation of mechanical energy that change in kinetic energy and change in potential energy together equal to zero if there is no drag. However, since we are told that there is loss of mechanical energy, the sum of kinetic and potential energies, the changes in kinetic and potential energies, actually equal to either loss or gain. So we need to use the formulas for change in kinetic energy and change in potential energy, which is what you see on the screen right now, by plugging in 15 as final velocity, 0 as initial velocity, 2 as mass, 10 as gravity, and negative 20 as delta H, because we are moving downwards. This is why delta H has to be negative. And all of that together should still equal to loss or gain. We get negative 175 joules, meaning because it's negative, it's a loss and not a gain. And this system lost 175 joules as drag and friction heat because there are no other ways that the ball could lose that energy. As discussed earlier, the total energy of a system never changes. If there is no friction or drag in the system, then the sum of kinetic energy, Ek, and potential energy, Ep, equals to total energy, Et, which is constant. So let's look at these two systems. First one will be a pendulum, which is a ball on a string that oscillates due to gravity. So right now we're holding the ball. In this box we'll have the green represents the potential energy, and red will be the kinetic energy. As we leave the ball, when the ball oscillates, the total energy, which is the energy within that rectangle, changes from being potential to kinetic, or something in between. As we can see, as the ball is at topmost positions, there is the most potential energy, while at its lowest most, there is mostly kinetic energy. Because potential energy, this is because potential energy is the energy that has potential to do something, in this case, to turn into kinetic energy and move. And as we can see, the sum of kinetic energy and potential energy at any given point of time equals to total energy, which is constant. Now let's look at the mass spring setup, which is similar to what we saw when we looked at Hooke's law. Again, we hold the block away from its resting position, and then when we release it, all the potential energy stored in that spring turns into kinetic energy as the block moves. Similarly to the pendulum, the sum of kinetic energy and potential energy in the system equals to total energy, which is constant at any given point of time, if there is no friction or drag. If we plot both kinetic energy and potential energy versus time for either of the system, we'll get the following. So if we release any of the two systems, we'll have potential energy at its highest positions and kinetic energy at their rest positions or lowest positions as possible. We can see that on the graph now that was created for us, that energy fluctuates from potential into kinetic. At any given point of time, if you add up the amplitudes for kinetic energy and potential energy, they will equal to total energy, which will be constant at any given point of time. Now let's talk about power. Power is the rate of energy usage, or power equals to energy divided by time. Similarly to velocity and acceleration, people who don't calculus can see that power is rate of change of energy as time changes, which is the first derivative of energy. Even though we don't have delta in front of E and T, it is kind of inferred. From the formula, we can see that power has the units of energy per time, or joules per second, which are known as watts, denoted by W. Since we know that energy equals force times displacement times cosine theta, where theta is the angle between direction of force and displacement, formula for power can be expressed as the following. Power equals force times displacement times cosine theta divided by time. But since that displacement divided by time is velocity, power can be written as force times velocity times cosine theta. Your physics data booklet has only P equals VF. So it would be wise to memorize the topmost formula and to remember that cosine theta also applies here as much as it does for energy. Let's look at this example. A horse walking at 1.75 meters per second is drawing a barge having a drag force of 493 newtons along the river. The angle the draw rope makes with the velocity of the barge is 30 degrees. Find the rate at which the horse is expending energy. So, since energy rate is the same thing as power, because we know that power is energy per time, energy used per time, we can use formula P equals VF cosine theta. Here we are told that theta is 30, force is 493, and velocity is 1.75, which gives us with power of 747 watts. Now let's look at efficiency. Efficiency is the ratio of output power to input power. As we can see in the formula, efficiency equals to work out divided by work in, or power out divided by power in. To understand this better, we'll do an example. Conversion of coal into electricity is through a following process. Coal burns to heat up water into steam. Steam turns a turbine, which turns a generator, which then produces electricity. Suppose the usable electricity from such power plant is 125 megawatts, while the chemical energy of coal is 690 megawatts. Find the efficiency of the plant. So right away we can, because it asks us for efficiency and it tells us power, we can use efficiency equals power out divided by power in. Power out in this situation will be power that we can use, or usable electricity. So power out will be 125. Power in is the total power that could potentially be used, but isn't necessarily being used. In this situation, it's the total chemical energy in coal, which is 690, which gives us efficiency of only 18%, or 0.18. Usually AB wants you to use percentages versus ratios. There is no definite rule which one you should use, whether you should use a percentage or you should use a decimal, 0 point whatever. However, it's more likely to see percentage within a question, which will come up later in chapter 8. So this was chapter 2, subtopic 3 for you. Tune in for the last section of chapter 4. See you there.